introduced this balance, which is nothing but a conservation of vorticity. And what we did, we introduced the importance of vertical velocities. Okay, and now we will explain how that comes about. You probably know already, what we should know already. But what is the importance for ocean dynamics? Okay? So what we did is we took the geostrophic flow, okay, and we added rotation. So we kept rotation in the beta plane, and we showed that using mass continuity, you can arrive to this balance. Whereas if you have an input of vorticity, for example from the wind, then the ocean responds by conserving the potential vorticity and moving, in this case, northward or southward, so changing its planetary vorticity beta. Okay. And that induces a meridional velocity, geostrophic velocity. So by conserving potential vorticity, the ocean is responding to this input of vorticity from the wind, generating a geostrophic current. So now we're going to see, so this is in the geostrophic interior, okay, where we have not introduced frictional effects yet. So if at the surface I have some wind stress, that will generate a vertical velocity, and then the ocean interior in geostrophic balance will respond by changing its planetary vorticity and inducing a meridional geostrophic current. But how the wind stress, the momentum flux, or any frictional force is transmitted to the ocean interior is through the Ethmoid layer, okay, that you know already. So this vertical velocity is generated at the base of the Ethmoid layer and induces the geostrophic velocity. How you go from the surface, for example, in the ocean, the surface of the ocean, to the interior geostrophic flow is through the Ethmoid layer. That we will see again today. I know you've seen it at least a couple of times, but you will see it again. And you will see it again for the importance for the ocean. Okay? And there are concepts that you know already, but we will put it in the context of ocean dynamics. Okay, so we'll talk about the Ethmoid layer. So usually in the ocean you care about the top Ethmoid layer, the upper Ethmoid layer. In the atmosphere usually you care about the bottom Ethmoid layer. The theory is the same, and we will see both. In the ocean is also important the bottom Ethmoid layer, but not for the large scale ocean dynamics. So our assumptions are going to be the usual ones. Okay, we have a surface where you have some velocity that is a function of depth, and then you have an interior ocean where you only have a geostrophic velocity. So the interior is in geostrophic balance. Whereas at the top you have your geostrophic flow plus a correction which is given by the Ethmoid velocity. This depth is the depth of the Ethmoid layer, so delta, where frictional effects are felt. Okay. And so the assumption is that delta is much smaller than the total depth of the fluid. We are in a Boussinesque fluid. We don't consider nonlinear time-dependent terms to make things easier, of course. And so this frictional layer in fluids, in the case of geophysical fluids, atmosphere, ocean, it's just called Ethmoid layer because of the person who made the first theory about it. Okay, so the equations that we had were the geostrophic ones. Okay, so this is just the horizontal momentum equations for the geostrophic flow. And then we had the hydrostatic balance, still using the hydrostatic balance, and mass continuity. Now what we're going to do is add a frictional term. And if we assume no accelerations in the fluid, okay, so if we look at the steady state, no, you don't see, oh, this one. Okay, so if you assume steady state, then this is the set of momentum equation with frictional effects on fields. Okay. So these are going to be my frictional terms. Okay. In geophysical fluids, the vertical component. In geophysical fluids, the vertical component is really the important one. Okay. Now, if you remember GFD, the very first classes that we took, we know the Newton's law of friction. We arrived to the expression for the Newton law of friction that gave me this dependence between the shear and the stress tensor, okay, related through the viscosity coefficient. So you can write this as rho nu. Okay. And in the case of the ocean, this viscosity coefficient will be the Eddy viscosity coefficient. Then you can write as this. Okay, the vertical Eddy viscosity coefficient, which is roughly 10 to the minus 1 or something like that. Okay, and that comes, of course, this comes from the Reynolds stresses, where you've seen the Reynolds stresses, I'm sure. This is minus U prime. Okay, I guess you've seen the Reynolds stresses in atmospheric dynamics or with agent. Okay, so that's how we can rewrite our frictional stress, which is now an Eddy frictional stress. Okay, we're not going to consider molecular the molecular coefficient, but the large scale Eddy coefficient for large scale dynamics. So what we can write is it in terms of mass. Okay, so we can work this and then dt by dz. Okay, this is tau. My frictional terms in terms of a mass of a fluid, and this is 1 over rho d by dt of tau, which is this one. Okay. And so this is a z. Okay. So this is how I can write my frictional stress term. So I can put it there in my set of equations as okay, so this is how I can rewrite my momentum equation with the frictional term. So these are going to be the equations that we're going to use, plus mass continuity and the hydrostatic balance. Okay. Now you can make a scale analysis here and look at the relative strength of the frictional terms and Coriolis. So you have F and a typical U, and you have AZ, then U over H squared, and one over the other. So this goes away, so you can introduce the no-dimensional number Z over A squared. This is the Ekman number, if you remember. Okay. And so this is telling us when frictional effects are important compared to Coriolis or not. So in the interior of the ocean, Ekman is small, okay? And so you can neglect frictional effects. So you're here. Whereas in the boundary layer, the Ekman number is on the order of 1. So it's comparable to the Coriolis effects. It's not much larger, otherwise you're not a geophysical fluid anymore. You're just a fluid in a pipe or whatever. Okay? So you want to retain Coriolis. So you want the Ekman number to be on the same order as Coriolis, not much larger. Otherwise you could neglect the rotation. So here in the boundary layer, frictional effects are important, and in the geostrophic interior, frictional effects can be neglected. And if you put some numbers there, H square is AZ over F, and AZ is roughly 10 to the minus 1, F is 10 to the minus 4, so this is 10 to 3 meters squared. So the typical, here I'm using H, here I'm using delta, sorry. So the typical depth or height of the Ekman layer in a fluid is something like 30 meters. It's just a rough estimate to understand that it's a few tens of meters in the top Ekman layer. In winter, in the ocean, the top Ekman layer can be 100, 150 to 100 meters, but in normal conditions, it's on the order of a few tens of meters. So it's very shallow. Okay? But it's very shallow, but as we will see, it's very important in order to transmit the momentum flux of the wind stress to the interior of the ocean. We don't care that much about the Ekman spiral, what is happening within the Ekman layer. We're not coastal oceanographer. Okay, the only reason why we are talking about the Ekman layer here is to understand what is the dynamics of the Ekman layer and how it can transfer, how it can connect the surface wind stress or the frictional effects at the surface or at the bottom with the interior geostrophic fluid. Okay, the details of the Ekman layer are not important here. So a few tens of meters, but crucial for putting in contact the surface to the interior geostrophic fluid. Okay, so now we can now we can, as we did here, we can define velocities are G, geostrophic velocities plus interior velocities. And also pressure is going to be the geostrophic pressure plus the pressure within the Ethmoid layer. So we use hydrostasy, as we said. Okay. So that dP by dz is equal to 0, also because we said that buoyancy is constant. Constant buoyancy? Yes, buoyancy. Constant, okay? So I add that. So the hydrostatic balance reduces to this. So in the boundary layer, the geostrophic contribution to pressure is equal to 0. Okay, because of the hydrostatic balance. And in order to satisfy the hydrostatic balance, then the contribution from the Ethmoid component also has to be 0, so that the hydrostatic balance holds. But the contribution from the Ethmoid layer to P everywhere else outside of the boundary vanishes, and so the condition that we will put is that this is equal to 0 everywhere. Okay. Because there's no contribution within the interior, okay, because all the Ethmoid paths are equal to 0. And so if the Ethmoid component, the Ethmoid contribution to pressure vanishes in the interior, then it will have to be 0 everywhere in order to satisfy the hydrostatic balance. So this is 0. So if we go back to the momentum equation, so there is a boundary layer in the velocity, but there is no boundary layer in pressure. Okay. So if we go back to our momentum equation, I can put this into a single one. Okay, I can put all of this into a single equation as this. Okay, so combining the two momentum equation. And so this is the frictional geostrophic balance. You have the geostrophic balance and the frictional balance. In the boundary layer, we only have the Ethmoid component and the balance between frictional effects and Coriolis, because there's no boundary layer in pressure. Okay, so this should be in the boundary. Okay, so now we can define a mass transport within the Ethmoid layer. Okay, so we can integrate over the Ethmoid layer. Okay, so we can integrate from 0 to minus h Ethmoid. Okay, integrated within this Ethmoid layer. Rho u Ethmoid. And if we integrate vertically here, this is tau at the top minus tau at the bottom. Okay. And this is what we're going to call ME. So the mass transport within the Ethmoid layer. Okay. Multiplied by rho, so this is a mass transport. Okay, so now our equation looks something like this. Top minus tau bottom, okay, within the boundary layer. And now if we consider a top boundary layer, the top boundary layer, the just a little bit. So we have a top boundary layer and a bottom boundary layer. Right? So here my frictional forcing is, for example, wind stress, and here at the bottom my frictional stress is bottom drag, for example. Okay. So for a top boundary layer, tau at the bottom is equal to 0. So I have tau top. Okay. And for the bottom boundary layer, tau at the top of the boundary layer is equal to 0, and I only have frictional effects at the bottom. And now if you rearrange this to make it clearly, perhaps, okay, what you get is that the mass transport, the total mass transport, here at the top, is 1 over F unit vector tau at the top. And for the bottom, you have E 1 over F tau B. Okay, so these are the mass transports for a top and a bottom boundary layer. So the top boundary layer only cares about frictional effects at the surface, of course, and the one at the bottom only cares about frictional effects at the bottom. Now we know that this is, for the case of the ocean, wind stress, okay, and this is bottom drag. And this is the mass transport within the Ethmoid layer, because remember that this is the mass transport integrated over the Ethmoid layer. So the total mass transport, which is what we really care about, the total mass transport, and then the associated vertical velocities that are produced. Okay. So in this case, it's nice to imagine. I'm never going to be able to draw this. Bit of imagination. Okay, getting there. This is the atmosphere, and this is the ocean. Okay, and this is the surface of the ocean. Okay, and this would be so the atmosphere on top and the ocean at the bottom. This would be the Ethmoid layer in the ocean, and this is the Ethmoid layer in the atmosphere. Of course, for the atmosphere is a bottom Ethmoid layer, and for the ocean is a top Ethmoid layer. Now imagine you have a wind stress blowing in this direction, so some tau x. Okay. So if you have a tau x, imagine that your tau y is equal to 0. Okay, there's only a zonal component tau y is equal to 0, that means that mx in Ethmoid is equal to 0. Okay. If you expand this, you will realize this is supposed to be bold m. So if tau y is equal to 0, the x component of the mass transfer is also equal to 0. And if tau x is positive, like in that case, then the Meridiano component, the y component of the mass transfer, is also positive for a top Ethmoid layer. And so this is already telling you what you already know, that the total mass transfer in the Ethmoid layer is at right angles to the wind stress in the northern hemisphere. Okay, F is positive. Something that you already know. Okay, so the wind stress, the total mass transfer is at right angles to the wind stress, and in the case of the northern hemisphere, when F is positive, then it's to the right. So if you have this zonal wind stress component, you will produce an Ethmoid mass transfer which is directed into the board or out of the board? Out of the board. So this would be the oceanic mass transport. Okay. But then imagine you are in the atmosphere now for a second. And if you are in the atmosphere, what you feel is a bottom Ethmoid layer. Right? And if you have a bottom Ethmoid layer, and then you look at this equation, and you have tau again. Now for the atmosphere, this tau is again the wind stress producing the drag. And you see that if you do this simple expansion, there's a minus here and there's a plus here. So for the bottom Ethmoid layer is the other way around. So for the bottom Ethmoid layer in the atmosphere, you have the same tau, because it's the same wind stress forcing the top Ethmoid layer in the ocean and the bottom Ethmoid layer in the atmosphere. So it's the same tau, F is the same, but there is a sign change. So the total mass transfer in the atmosphere, because it's the bottom Ethmoid layer, is at right angles to the wind stress, but to the left. Okay. And if you remember when you did GFD and you did the Ethmoid layers, you know that at the surface, northern hemisphere, you have the spiral 90 degrees to the right in the northern hemisphere, but the bottom layer is also spiraling up, and the total transfer is 90 degrees to the left, because it's like looking from the bottom of the ocean. So if you go swim and you lie down on the bottom of the ocean and you look upwards, then you will see the spiral going the same way as the top Ethmoid layer if you're looking from above. It's just turning things upside down. Okay. So if this is the mass transport in the Ethmoid layer from the ocean, and this is the mass transport in the bottom Ethmoid layer in the atmosphere, you clearly see from the equations that the two are equal and opposite, because it's the same wind stress causing this mass transport. Okay? So if there is no initial mass transfer in the Ethmoid layer, or in the interface of the ocean atmosphere, if suddenly you have a wind stress blowing in this direction, that will produce top Ethmoid layer in the ocean, bottom Ethmoid layer in the atmosphere. They don't need to have the same depth, because if you remember, the depth depends on the viscosity coefficient. Okay? But that we don't care about the details of the spiral within the Ethmoid layer. What we care about is the total mass transfer within the Ethmoid layer. And the total mass transfer doesn't depend on the viscosity or anything else. It only depends on the frictional term. And so the total mass transfer within the Ethmoid layer in the ocean and the atmosphere, they might have different depths, but the total transfer are equal and opposite. because they are forced by the same wind stress. Now I have a blue. Okay, and this is a plot of Meridiano Ekman volume flux. Okay, it's not this is a mass flux. Just remember this is a mass flux. Okay. Here I'm showing a volume flux. So this will be the Meridiano volume flux, so something like this. Zonal integrated over the ocean at the top. Okay. And so the bold black line is the total Ekman volume flux in the ocean. You will clearly see that there's a change in sign roughly at 30 degrees where you switch from westerlies to easterlies. So you have the this would be the westerlies, and then you have the easterlies blowing from east to west, and that will cause different mass transport. So here you have positive mass transport going northward, and here you have some negative mass transport going equatorward. Okay. And then you can look at the different contributions from all the different ocean basins. But the important thing is that there's a zero here, and so there is a mass transport to the north, and here there's a mass transport towards the equator. Okay. And that will cause this. That we will see in a second. That will cause a Ekman pumping. Okay, so now we go back to the continuity equation. Okay. In order to, now the flow is going to be no divergent. Okay, it doesn't have to be divergent. If you integrate the continuity equation within the Ethmoid layer, we integrate the continuity equation within the Ethmoid layer. And if you remember that ME is the integral of rho u dz, okay? So the total mass transport within the Ethmoid layer, and you put this in here in the continuity equation. You get to this, okay, by using the mass transport, the Ethmoid mass transport into the continuity equation. You get to this, which is equal to, this is minus at the top minus vertical velocity at the bottom. Okay, if you use this and you take the curl of this, taking the curl of this equation that we look for is just tau top minus tau bottom over f. Okay, just taking the curl of this. And so if you look at the continuity equation using the mass transport and then this equation taking the curl, then you see this that we're going to use equal 1 over rho. So taking this curl of tau top minus tau bottom over f. Okay. This is the continuity equation, but then this, the divergence of the mass flux, is equal to this, the curl of tau over f. So this continuity is also equal to this. Okay, and so for a top Ethmoid layer, this in the ocean, vertical velocity at the top is equal to 0. And so you have the vertical velocity at the base of the Ethmoid layer. So there is a vertical velocity associated with the total mass transport, which is divergent, sorry. And that vertical velocity is at the bottom of the top Ethmoid layer. Okay, minus minus is plus. This is 1 over rho curl of tau top is not 0, but tau bottom is 0. Tau top over f. And so this is the vertical velocity at the base of the Ethmoid layer associated with the mass transport in the Ethmoid layer, total mass transport, and the divergence of the mass transport. So you have convergence or divergence of mass transport in the ocean, and they will cause this, which is the zonally average vertical Ethmoid volume flux, that WB. Okay. So here, not tall enough. Here you have transport to the north, transport to the south. There is convergence. There will be a vertical velocity at the base of the Ethmoid layer. So if there's convergence, there's going to be pumping of water. So W is negative, you see here. And then here you have transport going to the equator. Then you're supposed to have some little transport going to the pole. That's divergence, and you have some vertical velocity associated with that. So this is the total volume flux, which has divergence and convergence regions, and associated with that is Ethmoid pumping. So this will be pumping, and this will be Ethmoid suction. And I can actually show you my very nice plot. So this is Ethmoid pumping from observations, so from a satellite, quick scan. You take the wind, you compute the wind stress, you compute the wind stress curl, like this, okay? You compute the wind stress curl from the winds, and then you simply calculate the vertical velocity associated with the Ethmoid vertical velocity. So here, positive, I switch the signs, so pumping meaning into the ocean is positive. and suction out of the ocean is negative. So you see these large regions of Ekman velocity down into the ocean and regions of Ekman velocity of suction upwards out of the ocean. And those are associated with the wind stress curl in the ocean. So the wind stress curl, this curl generates the Ekman velocity. And that's why I told you at the beginning that it's not really the wind stress that drives the ocean, but it's the wind stress curl. Okay? It's the curl that, through an Ekman layer and through the divergence of the mass transport within the Ekman layer, generates these vertical velocities at the base of the Ekman layer. And that vertical velocity at the base of the Ekman layer will put the interior of the ocean in motion, as we saw here. Okay? So this WB is nothing but this. Okay. So if you have some vertical velocities pushing down the interior of the ocean, pushing down some layer of the interior of the ocean and adding vorticity, then the interior of the ocean will respond by conserving potential vorticity. And in this case, it will start to move out of the board towards the equator. We will see that. Okay. So what really matters is the curl of the wind stress, not so much the wind. So now I can, using the derivation of the Ekman layers, I'm not going to do it again because you might fall asleep. So we can just have a look. Okay, so this is what we just talked about. Okay, so you can derive, you've all seen the boundary layer derivation at least twice. Okay, so we're just going to go through the derivations quickly so that we can see the difference between the mass transport in the bottom Ekman layer and the top Ekman layer, which is what we care about. Okay. So you take the momentum equations that we saw before, you take again mass conservation and the hydrostatic balance. Okay. The interior of the ocean is in geostrophic balance. Okay. And you can write the geostrophic balance in a single equation like this. And then there's the boundary layer correction, where you don't have pressure gradient. There's no pressure gradient, there's no pressure contribution in the upper layer, so there's no pressure boundary layer. You only have a balance between Coriolis and the frictional effects. Okay, so this. But this goes away. So you can put them together and the pressure gradient goes away with this. So if you do the total U minus the geostrophic U, the pressure gradients go away. And then you have to put boundary conditions to this. So at the surface, U and V are equal to 0. And as the depth goes towards infinity, then you reach geostrophic flow. So as you approach, as you get out of the boundary layer, then the velocity will have to be equal to the geostrophic velocity. You seek solution the usual way. You find this solution and blah blah blah, and you get an expression for U and V, okay, and the usual Ekman spiral solution. Okay, so this will be the bottom Ekman layer spiraling if you are at Okay, so if you choose a geostrophic flow which is positive and the vertical component, the Meridiano component is equal to 0, and you substitute that into the equations for the U and V for the two components, then you have a U and V which are the Ekman contributions to U and V. There are no 0, both of them. So even if there's no Meridiano component in geostrophic flow, you still have a Meridiano component in the Ekman layer, and that's how you get the spiral. Okay. So at Z approaches 0, so the bottom, we are in the bottom boundary layer. So as you approach the bottom and you substitute, you get that U and V are equal. So that means that U and V are equal and generate a flow that is 45 degrees to the left of the direction of the flow. Okay, so because remember we are at the bottom boundary layer, so 45 degrees to the left. At the top is 45 degrees to the right. And about this. So if you compute the transport and the vertical velocity of this bottom boundary layer, okay, again you generate the total transport V and U. Okay. You get this expression, and the total transport, which is what we looked at before, is simply giving you again the expression that we saw a few minutes ago. And if you want to interpret the balance in the bottom Ekman layer, you have the frictional force is balanced by Coriolis. Okay. So frictional force is balanced by Coriolis, and the total transport is 90 degrees right angles to the force. So that would be how to visualize the forces and the net transport in the bottom boundary layer. If you want to look at the vertical velocity associated with this bottom boundary layer, okay, you take again the continuity equation, you substitute for U and V, and you get to this expression, okay, where this is, is that correct? That's vorticity. So the geostrophic vorticity of the interior of the flow. Okay, so for a bottom Ekman layer, you substitute again, you know this, that's equal to the curl of tau. Okay, I removed it. So this is what we saw before, generally, for the top and for the bottom. But now if you substitute for the bottom Ekman layer, you realize that this is equal to D is the height of the bottom Ekman layer, and this is the vorticity of the geostrophic flow above of the Ekman layer. So the vertical velocity at the bottom of the Ekman layer depends on the vorticity. That depends on the vorticity of the interior geostrophic flow. Okay? So the divergence of the interior geostrophic flow has vorticity, and that's the input of vorticity for the bottom boundary layer generating this vertical velocity. I guess you've seen this before. Okay, and so the vertical velocity at the top of the bottom Ekman layer, this one, arises because of the frictional induced divergence of the flow in the Ekman layer, and that is proportional to the geostrophic vorticity of the interior geostrophic flow. Then if you do again the same thing for the surface boundary layer, okay, it's exactly the same but upside down. Take the same set of equations, you do exactly the same thing, and then you give the boundary conditions. Now the boundary conditions are at z equals 0 at the surface you have the wind stress, right, which we can express it that way. And as z goes towards minus infinite within the boundary layer, then you approach the geostrophic velocity. So that is going to be the bottom boundary condition. You solve again the same way, and you obtain the same expression for the velocities within the Ekman layer spiraling. So the boundary layer correction depends only on the surface stress and not on the interior flow. Okay? So the bottom boundary layer depends on the divergence of the interior geostrophic flow, whereas the top Ekman layer depends only on the surface wind stress. Okay? It doesn't depend on the interior geostrophic flow. It's the other way around. The interior geostrophic flow depends on the surface boundary layer because of the vertical velocity associated. Okay, you solve again. What happens at z equals 0? So at the surface, you solve at z equals 0, and again you find the usual spiral. So what you get, the surface is velocities that are equal, u and v, 45 degrees to the right of the surface wind stress. Okay, this. So the geostrophic flow is 45 degrees to the right for F positive. Okay, so you can actually think of summarize this, the top of the Ekman and the bottom Ekman layer. And the only thing that you need to care about is the wind stress of the surface and the interior geostrophic flow. Okay? The surface wind stress will generate this mass transport and vertical velocities at the surface Ekman layer. And the interior geostrophic flow, the divergence of the interior geostrophic flow, will generate this Ekman pumping at the top of the bottom Ekman layer. Now what we really care about, as we said, is the total transport and the vertical velocities. So as we did for the bottom, you can integrate the total mass transport or the total transport in the top Ekman layer, which is proportional to the wind stress. And as you see, u is tau y over f and v is minus tau x over f. So they are perpendicular to the wind stress, okay, and 90 degrees to the right in the northern hemisphere if f is positive. Again, the geostrophic flow is divergent, so you take continuity, you integrate, as we did, and vertical velocity is 1 over f curl of tau. Okay, so that's the Ekman pumping at the surface, at the bottom of the surface Ekman layer. Okay, so what we will see the next time, so I went fast because you've seen it 2 or 3 times already, so you can read again a different way of deriving the same thing if you want. So now we can start developing the theories of the large-scale wind-driven circulation, okay? Because what you have now is, this is my ocean, okay? So I have an interior geostrophic flow here, okay? And now how do I set up an interior geostrophic flow? We've seen that if you have a wind stress, tau, and if you have a curl in tau, then you will have a vertical velocity associated with that curl of the wind stress. And if you have a shear in that vertical velocity associated with the curl of the stress, that will set up a motion inside of the ocean, in the interior of the ocean. So you have an input of vorticity, and that input of vorticity has to be conserved, and it does so by changing planetary vorticity and generating a meridional geostrophic flow in the interior. Okay? And so from this, that is called Virtual balance, then you can start thinking about the interior wind-driven circulation in the ocean. Okay? The only thing that drives the ocean here is the wind stress. So it's totally wind-driven. Okay. But now if we stay a second talking about the Ekman pumping, okay? So we talked about the first time, I think, about the how you can close the meridional Evertonian circulation. You can close the meridional Evertonian circulation through diffusion, but that is not enough. And so you also need upwelling of water to the surface. And you have upwelling of water to the surface by Ekman upwelling. And you can have Ekman upwelling because in the Southern Ocean, because if this is the Southern Ocean and this is north, okay, south and north, this is the surface of my ocean, and I have strong wind stress blowing westward, okay, so out of the board. So there will be an Ekman layer here developing, and there will be a total mass transport within the Ekman layer, which is directed to my right, okay, because we are in the southern hemisphere. And so the total mass transport is equatorward. And here I have a continent, so there will be divergence, and so there will be a vertical Ekman pumping associated with this large-scale mass transport. And so I have Ekman pumping in the southern hemisphere. Okay, so upwelling that you can see here. Okay, this blue. And that is bringing up a lot of water that sunk in the northern latitudes, traveled all the way to the southern hemisphere, and then is upwelled by Ekman pumping in the regions of the Southern Ocean. So you can upwell all of this, well, most of this North Atlantic deep water through Ekman pumping in the Southern Hemisphere. There's another reason why Ekman pumping is so important. Okay. And so you've probably seen this already, but there's a few cases of upwelling. This is coastal upwelling, okay, because there is a coast here that causes the divergence of water. But there's more coastal upwelling regions. So suppose you have a wind that is totally meridional, so tau x is equal to 0. And therefore the meridional component of the mass transport is equal to 0, and the zonal component is positive for a positive tau y. Then the net transport will be to the left of the wind direction. Continuity requires that you have an inflow from this divergence because you have a continent. And so if the wind is blowing parallel to the coast, which is on the right of the wind, this causes an Ekman transport, which is away from the coast. And water has to be replaced somewhere by an Ekman pumping. And so that's called coastal upwelling. And now I wanted to show you plots. So where does this occur? Go back to the wind stress plot. This. Okay, look at the meridional wind stress. Meridional wind stress. This is the climatological meridional wind stress from satellite. Here is negative, here is positive, here is negative, and here is positive, and here is also positive. Okay? So what you have in those regions is a situation where the wind is blowing almost parallel to the coast, okay, in these regions. And so here in the southern hemisphere, the tau y is positive, but we are in the southern hemisphere, so the net transfer is going to be to the left, so away from the coast. Here in the northern hemisphere, tau y is negative, but f is positive, so again, the total mass transfer is going to be away from the coast. So, and the same thing here, here, and here. So in this, mainly these four regions, there's going to be a lot of mass transfer away from the coast and a lot of coastal upwelling. Okay. Also here, but not that much because the coast is smaller. So these four regions will be major regions of coastal upwelling. As I will show you in a second. And you can see this region of coastal upwelling if you look at a satellite image of chlorophyll in the ocean. Okay, chlorophyll is, so where you have a lot of chlorophyll, that means that there's a lot of chlorophyll being brought up from the subsurface to the surface through upwelling. Okay. And you have a lot of chlorophyll, so light blue means a lot, and dark blue means not that much. You have a lot of chlorophyll, even going to yellow and green colors, along the coast of Southwest Africa, Northwest Africa, California, and Peru, Chile. Those are the regions of large-scale coastal upwelling. Okay, so those regions of coastal upwelling are very important, not just for biology, also because of biology. I mean, at least these three places, the Benguela upwelling region, the Peru-Chile upwelling region, and the Northwest Canary upwelling regions are the three regions with the largest fisheries in the world. I think there's something like 80% of fishes are caught in these three regions, okay, because of this large-scale upwelling. A lot of nutrients are brought up to the surface, photosynthesis, and lots of fishes and lots of fishermen. So it's very important for society, for biology, but also for the physics of the ocean, and also for the physics of ocean-atmosphere interactions. Because when you bring up subsurface water, you bring relatively colder water to the surface. Okay? So if you look at a map of sea surface temperature, you will see that sea surface temperature is relatively cooler in this region of upwelling. Okay? And if you have temperatures that is relatively cooler, that will have an effect on the heat fluxes with the atmosphere. In terms of temperature, precipitation, humidity, clouds, cyclone developments, so on and so forth. So these regions are very important not just for the ocean circulation and biology, but also for the couple ocean-atmosphere interactions. The problem is that these regions are difficult to reproduce in models, because in this upwelling, it seems all very simple, it's just a few equations, but then the actual processes going on in upwelling regions are complicated. Because there is large-scale dynamics like this, but there's also small-scale dynamics. There's a lot of eddies, filaments, vertical mixing processes, interaction with the atmosphere, okay? And so it's difficult to represent, and there's a lot of well, you need a high resolution to represent this, also because of the coastal resolution that you want. Okay? So if you don't have the right resolution in the coast, you might place the wind stress in the wrong position, and that doesn't generate the correct upwelling along the coast. Okay? So it's very difficult to represent in climate models, actually. Well, you do get it, but you get it wrong. Okay? These are two maps of sea surface temperature biases. And so what I did here is take the many climate models run for the last century. And then you average all those climate models, you do a multi-model mean, and you take the difference with the observations. Okay? So it's basically trying to understand how good they are in terms of representing sea surface temperature. This is the present-day generation of climate models, CMIP 6, and this is the previous one, CMIP 5, okay, something like 7 or 8 years ago. So this is sea surface temperature, the difference between models and observations. Okay? So it's doing quite good in many places, but then you see a negative bias here, and that's because models tend to represent the Gulf Stream, the western boundary currents, in the wrong position. So if you switch the position of the Gulf Stream, you suddenly create a large bias in sea surface temperature. There is a bias in the Southern Ocean, okay, a warm bias in the Southern Ocean that's related to upwelling, not enough or correct upwelling. There's a bias in the cloud coverage, changing the sea surface temperature. But then you notice that there are large regions of biases that are located in the coastal boundary regions, okay? Especially Venezuela, Peru, Chile, and California, not so much in the northwest. So the largest bias actually in climate models today are located in coastal upwelling regions, because of the inability to represent all the processes going on in those regions. So it seems very simple from a theoretical perspective, but actually to represent that in a climate model is very difficult. And this large bias that goes, I think, up to 6 degrees, okay, so it's huge. This large bias, 6 degrees in the Benguela upwelling region, causes large differences in the representation not only of ocean dynamics but also the atmosphere, the cloud coverage, and the surface winds, coastal winds, precipitation of the land, not just about the ocean. Right? I usually think about the ocean, but that has implications of the land as well. So very problematic for climate models to represent coastal upwellings because of many reasons. Not just, you don't need just to improve the ocean, you also need to improve the ocean-atmosphere interactions, the clouds, for example. And then, of course, you have, so this would be an example of what we know the coastal upwelling. So this would be Northwest Africa, for example. You have the meridional winds blowing towards the equator, total mass transport away from the coast. So the total mass transport is away from the coast, and you have a vertical velocity associated with that divergence, and you create a coastal upwelling there. You can have equatorial upwelling, of course, and the boundary is not a physical boundary, it's not a coast, it's not a continent. What you have at the equator, the boundary is F. Okay? So the boundary is F, where F at the equator switches sign. Then if you have winds blowing into the board, you have the trade winds, you have Ethmoid transport away from the equator on both sides, because F switches sign. And so you have upwelling at the center towards the equator. and I think that's it. Okay. Well, you've seen all these cases of upwelling, so I'm not going to go into too many details. You can read what I wrote here. It's just another way of describing the upwelling regions and the different cases of upwellings. Okay. I didn't talk much about the Southern Ocean upwelling, but is another coastal upwelling, okay, which is probably, for the large scale ocean dynamics, is probably the most important, because it brings up all these deep waters to the surface and closes the upper set of the Meridiano circulation. And also by bringing up all this North Atlantic deep water that ventilates the ocean and gets CO2 or releases CO2, gets heat or releases heat. So there's a lot of flux exchange at the surface through this Ethmoid pumping associated with the Ethmoid layer. Okay, so next time we'll start looking at the how you form a wind-driven jar, starting from this, from the Ethmoid pumping or Ethmoid velocity. Any question? No interaction? No comments? I really like the way you introduced the Ethmoid layers compared to the previous ones. Or something like that. What I can tell you now that I'm done is that I was awake until almost 1 o'clock in the morning to make this plot. At the end, it was it was a battle between me and the data set. Okay? I spent 20 seconds on this plot, I know, but it took me 6 hours to do it. But it was worth it. That's nice. Because I had one from model, but then I thought it's nice to show observations, right? Because I've been showing observations so far. So I want to compute the Ethmoid pumping from the observations. And working with models is so much easier. You have a regular grid, you know the grid size, you have continuous data in space and time. Working with data is a bit more difficult. But I managed. You probably don't care, but I'm happy. Okay. I'll see you on Monday. Bye-bye.